This talk is on evaluating the dry cell versus silver cell. It's part of 9.2.4 from the HSC Chemistry course. In particular, we're going to be evaluating the chemistry of both these cells, their cost and their practicality, what impact they've had on society, and what impact they've had on the environment. The first cell we're going to look at is the dry cell. This is the standard sort of cell you see in most appliances, AA, AAA, C and D style batteries, and its structure looks something like this. First you have the positive terminal, which is actually a metal cap on top of some carbon graphite. The carbon graphite acts as an inert conductor. You've got an insulating seal to separate the anode from the cathode. You've got an ammonium chloride paste, which acts as one of the reactants in the cell, but also as the electrolyte. You've got a zinc cylinder. The actual casing of the battery or the cell is made of zinc, and that is the anode in the reaction. You've got a mixture of carbon paste, manganese dioxide, and ammonium chloride, which acts as the cathode reactants and also electrolyte. You've got the carbon graphite rod, which acts as the conducting cathode, and you've also got the negative terminal. So it's some quite complicated chemistry inside a dry cell. Let's see how it actually works. The first thing that happens is a cathode reaction. We know at the cathode from our rules. We've got anox and a red cat. Reduction occurs at the cathode, and this is the reduction equation that occurs at the cathode. We have aqueous ammonium ions reacting with the manganese dioxide. Don't forget the manganese dioxide and ammonium ions are in this region here around the cathode, plus water. It is a paste inside here. It's not a liquid, it's not an aqueous solution really. It's more of a paste. There is some water inside there, and electrons, those electrons coming from the anode reaction. So the ammonium ions, the manganese dioxide, the water and electrons, they cause the formation of products: manganese hydroxide, it's manganese 3 hydroxide, and aqueous ammonia. And that's quite a complicated equation to try and remember. We'll try to learn a memory trick in a minute. And the memory trick we came up with a few years ago was never hate mangoes, watery monkey nuts. And you have to use your imagination to see where this comes from, but hopefully it will help you remember this equation. First of all, we've got never hate. It comes from the NH4+, which sort of looks like NHAT, which sort of looks like never hate. So that's never hate. The mangoes comes from the manganese dioxide or manganese 4 oxide. MnO2, it's got 2 O's, hence there are O's, hence mangoes. Next you've got water E, and water E is just the water molecule and the electron, as in water E. Finally, you've got monkey, which is the manganese 3 hydroxide, and monkey rhymes with 3, that's how you remember that one. And finally, you've got nuts, because NH3 ammonia doesn't look like anything at all, but we thought nuts would fit in a little saying. So never hate mangoes, watery monkey nuts. That's the way that I remember the cathode reaction in a dry cell. You've also got the anode reaction, which is an oxidation reaction. Before we get to there, if you want to, you can simplify that equation. I'd prefer to use the whole equation, but you can simplify it, because what's really happening is a manganese 4+ ion is being reduced to a manganese 3+ ion. If you go through and do your oxidation number calculations, you can prove that's manganese +4 and that's manganese +3. That's the species that's actually being reduced. At the anode, you've simply got zinc oxidation. So the zinc casing itself is being oxidized. And what happens is, for this cell to work, you've got to plug it into something. And in the process of plugging it into something, the device you plug it into becomes the electrical contact, and electrons then flow from the negative terminal at the anode, where the zinc's being oxidized, right around to the positive terminal at the top. Those electrons go into the carbon graphite cathode, which is this thing down the middle, and those electrons can then leave that cathode into this paste here to cause this reaction to take place. And a device you want to plug in might be your portable ear trimmer of many possible things. The next thing we can look at now is, well, let's look at the chemistry. We have to evaluate the chemistry in this particular part of the HSC course. We've got to evaluate, and evaluate means look at the positives, negatives, and make a judgment. So the first thing we're going to look at is the positives of the dry cell chemistry. And the positives are, well, the first big positive is it works. It produces a useful voltage of about 1.5 volts, and that means you can use it to power a device. Second of all, it hasn't got a liquid electrolyte, and this is one of the first cells that was produced with a non-liquid electrolyte, which meant it was portable. You could make portable electronics with it. If you've got a liquid electrolyte, you can't turn it upside down or tip it because it might spill. This cell was able to be transported and used without that concern. So it was the first portable cell, And finally, the chemicals are non-hazardous. None of the chemicals here are particularly dangerous, and therefore it's a fairly safe chemistry. However, this cell does have some disadvantages. That's what we're going to look at now. And they're all very important. And if you understand the chemistry of this reaction here, which is why I'm trying to make you memorize the whole reaction, it's the problems with this reaction, as you see it when it's spelled out in full, which helps to explain the disadvantages of this cell. First of all, the ammonium chloride, which is being used as the electrolyte, is actually slightly acidic. And zinc being a reactive metal, the ammonium chloride actually reacts and corrodes the zinc, which means after a long time the casing can develop leaks. And you've probably seen old batteries and you can see they've got a crust of salt on the outside. That's because the zinc casing is leaked and some of the paste has leaked out, causing a deposit of salt on the outside of the battery. The second thing is the ammonium chloride is actually the electrolyte in this cell. It transports the ions from anode to cathode and vice versa, completing the circuit and maintaining charge neutrality, allowing the cell to run. However, if you look in the reaction again, the full reaction, you'll see that the ammonium ions themselves are actually part of the reaction. They're actually being consumed. The ammonium ions are being turned into ammonia, which means over time the electrolyte concentration drops. The electrolyte's being consumed. And something we talked about when we looked at galvanic cells, the galvanic cells, the voltages that we look at, have to be done in standard conditions of 1 mole per litre solution. Now this isn't necessarily a 1 mole per litre solution, but the reason why standard cells need to be set up in 1 mole per litre is because concentration affects your voltage. And as the concentration of ammonium chloride drops, that means the voltage of the cell drops over time. So these don't have a very stable voltage. Their voltage does drop over time because this ammonium is being consumed, and therefore you get less efficient transport of ions between anode and cathode. Finally, even though the ammonia that's being produced is aqueous here, if enough ammonia is produced, it can form gaseous ammonia, and that gaseous ammonia, obviously gases take up more volume, and therefore that can cause some pressure inside the cell, and you sometimes see old batteries which are sort of swollen up, and that's because the gaseous ammonia inside has swollen the battery, and that can damage the battery and mean you can't use the battery anymore. So that's the negative side of the chemistry of the dry cell. The other aspects we had to evaluate as far as the dry cell was concerned was cost and practicality. And as far as cost is concerned, it's a very cheap cell. So that's a big positive. It's a very, very inexpensive cell to make. In terms of practicality, it's portable. It can be made in a fairly small size, which means it can be used for a range of portable devices such as torches and radios. The one downside of its practicality, it's not a rechargeable cell. The reactions are not easy to reverse in this cell. You can't plug these batteries back into a charger, and therefore they're not rechargeable. Rechargeable batteries have a slightly different chemistry inside. They're not the standard dry cell battery. Impact on society, we've got to evaluate the impact on society. Rather than thinking positive and negative here, because that would be a very hard argument to make, instead we're going to think about a different sort of evaluation of impact. We're going to look at how much it impacted on society. And what I'm going to suggest here is that it had a major impact on society because it was the first portable cell, which meant it led to the first portable electronics. That was a major impact on society. And finally, impact on the environment. The impact on the environment was quite low. The chemicals are non-hazardous, and therefore there's not much concern about the chemicals. The only downside, if you're looking for a negative, is the fact that these batteries, because they're not rechargeable, they just get put into landfill, and they do make a significant contribution to landfill, which has a negative impact on the environment. But overall, it's fairly low impact on the environment compared to many other products. And that's the end of the dry cell. So let's start looking at the silver cell. We have to evaluate them in comparison to each other. So we've seen how the dry cell works. We've looked at the positive and negative of the dry cell. Let's look at the silver cell. And the silver cell are the sort of cells you often see in very miniature devices like watches, because they can be made into a fairly small size. The structure is something like this. You've got the negative terminals at the top, and it's a stainless steel case. You've got an insulating seal separating anode from cathode. The positive terminal is also part of the stainless steel case. At the cathode, you've got a silver and silver oxide mixture that makes up the cathode. You've got a potassium hydroxide electrolyte in a porous medium. So once again, it's not liquid, it's just this potassium hydroxide which can transport ions in a porous medium. And finally, you've got zinc and zinc oxide mixed together to make up the anode. So the chemistry is quite different to the dry cell, but once again, you've still got the same basic features of a galvanic cell. You've got an anode, you've got a cathode, and you've got an electrolyte, and obviously when you attach it to a vise, that's when you get your electrical contact connection. And let's look at the reactions here. First of all, we've got the anode reaction, and what's happening in the anode reaction is that zinc reacts with some of the hydroxide ions, and the hydroxide ions are coming from this potassium hydroxide in the electrolyte here. So the zinc is reacting with the hydroxide ions in the electrolyte, and that forms a zinc oxide, water, and electrons. So what you can see here, the zinc has gone from an oxidation state of 0 to an oxidation state of +2. So it's the zinc that's being oxidized in this process and giving up electrons. Those electrons leave the anode and travel through a device which you might plug in, and this is a device I found on the internet the other day which I thought was quite bizarre. It's a portable record player. I have absolutely no idea where I would use that or how you'd find that useful, but in case you wanted a portable record player, there you go, you can buy them. And that would complete the circuit between the anode and cathode. Electrons would travel out of the anode through your portable record player into the cathode, and at the cathode what happens is the silver oxide reacts with some of the water from the electrolyte, because there's water in this electrolyte as well in that porous medium, and the 2 electrons that came from the anode, and that turns the silver oxide back into silver and hydroxide ions. So you can see here that silver's gone from an oxidation state of +1 to 0, so it's a silver that has been reduced. And throughout the process, hydroxide ions complete the circuit by travelling from the cathode to the anode. Now let's look at the positives of the chemistry. Similar to how we looked at the positives and negatives of the chemistry of the dry cell, this is the positives and negatives of the chemistry of the silver cell. So first of all, a big positive, especially compared to the dry cell, is the chemicals do not corrode the cell. You've got a basic solution here which won't corrode metals, and you've also got a stainless steel case which is fairly unreactive, and therefore the chemicals don't corrode the cell. There is no liquid leakage. Similar to the dry cell, there's no liquid electrolyte, which means it's portable. And this is probably the big feature compared to the dry cell. If we look at the 2 reactions, the oxidation reaction and the reduction reaction, you can see that in the oxidation reaction, hydroxide ions are being consumed and water is being produced. But it's the opposite in the cathode reaction, the reduction equation. You've got water being consumed and hydroxide being produced. So that means every time zinc is oxidized here and consumes some hydroxide ions, at the same time the silver oxide is being reduced and producing hydroxide ions, and therefore the concentration of these hydroxide ions, or the concentration of electrolyte, remains constant because it's produced at the same rate as at the cathode as it's being consumed at the anode. And that means the voltage remains stable over a long time, which is very important for electronics because they need stable voltages. So this was a very important aspect of this particular cell's chemistry. If we look at the negatives aren't quite as extreme as for the dry cell. The big negatives are, first of all, silver is expensive. Silver, the chemical, is an expensive chemical, which makes the cell relatively expensive. The potassium hydroxide is a basic substance and it's quite caustic, and it can be harmful if the cell is damaged. And once again, this cell is also non-rechargeable, which means you cannot reuse this cell, which is a negative for the chemistry. Looking at the other aspects of the cell, we're looking at cost and practicality, impact on society, and impact on the environment. First of all, cost. We said before the silver was expensive, which makes the cell relatively expensive. They're still not astronomically expensive, but comparatively they can be expensive. And one of the big features of the cell is they can be made quite small. They can be used for miniature electronics, so that's a practicality issue. They can be used for quite small electronic devices. Impact on society, you might argue it didn't have as much an impact on society as the dry cell, because the dry cell obviously was the first portable cell and therefore revolutionized portable electronics. But because the silver cell can be made small, it had a significant impact as well on its own, because it could be used for miniature devices such as watches and hearing aids and things like that. Impact on the environment, once again it's fairly low, but probably a little bit greater than for the dry cell. It is a smaller size, so bulk landfill is not quite as much of an issue, but you do have caustic potassium hydroxide inside there, which is an environmental concern. And silver, it's expensive, it's also a heavy metal, so you've got to be careful about how you dispose of it, but often places try and recycle the silver out of silver cells because it's expensive, and therefore it can be worthwhile trying to recycle that silver. So we've seen the dry cell burst the button cell, and we've seen the positive and negatives of the chemistry, cost, practicality, impact on society, and impact on the environment, and that's because the HSC syllabus wants us to evaluate those things. We had to gather and present information on the structure and chemistry of a dry cell and evaluate in comparison to the button cell in terms of chemistry, cost and practicality, impact on society, and environmental impact. So what you need to do as an activity, as a summary of this, is to comparatively evaluate each cell in terms of these criteria. But the one that is the most important and the one you have to spend the most time learning is the chemistry, and for two reasons. First of all, this is a chemistry subject, so you need to fully understand the chemistry of both those cells. You need to know the cathode reaction and the anode reaction of each. And if you know those reactions, the rest falls into place, because most of the things we discussed in terms of the positives and negatives of the chemistry, which is something you have to evaluate, if you know those equations, you can explain the positives and negatives of the chemistry. For example, the dry cell, you can explain why the electrolyte's consumed. You can explain the production of ammonia. You can explain why the zinc case corrodes. For the silver cell, you can explain why the voltage stays constant, electrolyte concentration stays constant. So if you understand that chemistry, everything else makes more sense. And the rest, cost and practicality, impact on society, environmental impact, you need to know them and you need to be able to evaluate them, but they're not as important as the chemistry. So know them all, but have a big focus on the chemistry.